So if we're talking about derivatives of exponential functions, e to the x, then there's this really cool pattern that people notice. So specifically, if I'm taking the derivative of, say, e to the 5x, there are lots of formulas in our textbook, but I said we don't need to memorize new formulas, we can just use our chain rule. So if I put my box around the 5 of the x, then the derivative of e to the 5x is going to be still e to the 5x, that's the derivative of the outside, times 5, that's the derivative of the inside. So we're going to get 5 times e to the 5x. And if I do that with a different constant, let's try e to, say, the 7x. Let's put my box around my 7x, so it's going to be e to the power doesn't change, times the derivative of whatever's inside the box, so derivative of 7x is 7. So I get 7 times e to the 7x. And people did a few of these and they realized, hey, there's a pattern here that never changes. Specifically for any constant k, if we have y equals e to the kx, then the derivative of y is going to equal k times e to the kx. Now this is one of the formulas in the textbook that I said we don't necessarily need to memorize. But there's something even more interesting here. When people did this, they realized, hey, what is this e to the kx? That specifically is equal to y. This is y from over here. And so I could actually write y prime. I can write my formula of y prime equals k times y. Interesting, right? So the derivative is always going to be equal to that constant times my original function y. If we're dealing with exponentials, this is a very special case, just dealing with exponentials. Okay. So we came up with this formula, and we thought that's a pretty cool formula. And this is actually what we call a differential equation. So a differential equation, we have an entire branch of mathematics devoted to differential equations. But the simple definition is anytime we have an equation that involves our original function and its derivative. So again, this is our original function y. This is the derivative of y prime. We have an equation that actually relates them. Now we can go a little bit further in our relationship. Let's try a few more derivatives. Let's now take the derivative of, say, 10 times e to the 3x. So I'll still put my box around the 3x. The 10 is just a coefficient, so it just comes out. Then I'm going to have e to the 3x again times 3. Or in this case, it's going to be 10 times 3 times e to the 3x. And we realize, oh, this pattern is actually going to continue forever and ever. If we let c and k be constants, okay, any constants, and let's let y equal some coefficient c times e to the kx. If that's the case, then the derivative of y is going to be equal, let's look at our pattern, the coefficient, the constant c, is still going to be there. Whatever constant or coefficient we times x by up in the exponential function, that's going to come out. So c times k times e to the kx. And once again, people looked at this formula, which we're not going to memorize, we'll just use the chain rule every time. And they looked at it and they said, hey, look, this c and this e to the kx, if we put those together, that's our original function y. Isn't that the same thing? C times e to the kx. And they said, we can write this as a general differential equation. So in general, y prime equals k times y. So if we start off with this y equation, then the derivative will be k times y. Now this is interesting. we're seeing patterns, but what if we want to go about this backwards? This is where we truly look with differential equations. So what we do is we say, now if we start with an equation where y prime equals some constant times y, then we know that y is going to equal some constant which might not have been in the original problem times e to the kx. So we did all this, we noticed all these patterns so that we can work backwards. So what we're actually going to do is we're going to find examples like this, where we want to find a function y equals f of x such that we have this differential equation. So we start with a differential equation, an equation that involves y and its derivative. And then we want to get back to, well, what would our original function have been that lets us do this? So we're going to start with our result we found up above. So if y prime equals some constant times y, then we know that y is equal to some other constant times e to the kx. So in this case, this is my k. Okay, because it said if we start with y equals k to the y, or y prime equals k to the y. So we can say that y is going to equal some unknown constant c. We don't actually know what this constant is because it would work with many, many constants. Okay. Times e to the kx, so e to the 5x. So we know that y is going to be something in this format. But how do you decide what that c is? Is that c going to be a 1, a 2, a 3? Well, any of those values of c would give us this differential equation of y prime equals 5 times y. How do we determine what that c is? Sometimes we'll leave it as a c if we don't know, but sometimes they'll give us what we call initial value. So this f of 0 equals 7, this is our initial value. Its job is to help us find the specific value of c that we want for this equation. So it turns out that any value of c would give us this differential equation. But sometimes we're interested in a specific value c, and this initial value is going to let us find that specific value of c. So what we'll do is we'll say now that f of x equals some constant c times e to the 5x. And we know that f of 0 is supposed to equal 7, so solve for c. So in other words, 7 is supposed to equal c times e to the 5 times 0. So we put in x is 0, y is 7. Now e to the power of 0 is 1. So 7 equals c times 1, or c equals 7. So my final answer is that y equals 7 times e to the 5x. And you just solved a differential equation.